Ohayou gozaimasu. Good morning. I want to start off with a question. Do you think AI will beat the world's best hackers? I get that question a lot. People ask it because they see software runs everything, and it's getting deeper and deeper, and yet we can't check it, we often don't understand it, and we have difficulties trusting it. And so we start thinking, what if we add in more automation? What if we don't just use AI to write the software? What if we can use it to automatically check the software? Well, doesn't that also mean, of course, that AI is replacing the hacker? This is what people keep asking me, and I want to start answering those questions in this talk. I think the answer is going to be a little bit surprising. What we need to do is start building systems that have autonomous loops in them that can learn from failures, that can help AI systems provide value, and that can help people train to get better as well as train the models themselves. So when people ask me, do you think AI can beat the world's best hacker? I have to pause and think, is that really the right question to reach that level of trust? But before we get into that, let's first look at one of the world's best hackers. Meet George Hotz. Back in 2007, the original iPhone comes out. It's sleek, it's sexy, but it's locked down. It only works with one US carrier, AT&T. George was just 17 and he wanted an iPhone, but he didn't want to change his carrier. So he did what hackers do. He didn't figure out how to change his carrier. He said, I want to change the phone. So he digs in and he figures out that the key to the entire lockdown is the baseband processor. He sees that the baseband processor is what enforces that phone to be locked into a particular carrier, and he thinks, how can I overcome this? So he does something actually kind of unusual. He actually digs into the hardware, and he solders on wires and glitches the baseband processor just right to put it into a newborn state. The phone boots. George gets on YouTube the next day and says, hi everyone, I'm GeoHot. This is the world's first unlocked phone. GeoHot flipped the script. He did what hackers do. They bend the machine. They don't bend to the will of the machine. They make machines do what they intend them to do. And so when I get this question, will AI beat the world's best hackers? I start thinking, well, first, do we think it's going to beat GeoHot? Do you think so? Maybe. I have my own opinions. But I think that's the wrong question. I think even if it could beat George Hotz in hacking, the real question we want to talk about is, will we be able to trust AI hacking in the real world? Imagine we have this autonomous loop, these advanced AI systems everyone talks about. Are we going to let them run our airplanes, our cars, our banking systems, our critical systems? Would you feel safe? If AI can beat the world's best hacker, in some ways that's just a parlor trick. The real question we need to be thinking about is, well, what then next? Will we trust it? And so after spending decades doing this, I think that there's really three core things that we have to get right to be able to trust AI hacking in the real world. And I advocate this type of thinking I call loop-based thinking. Let me explain. I think there's three things that we have to get right. The first one is the autonomy itself. What is this autonomous loop for how the systems are actually going to work and help secure the future? The second one is the adoption loop. What happens when autonomy hits real organizations? Are they going to go and put it deeply into their pipelines? Is everything going to be AI? Or is it going to be different? And the third loop is the improvement loop. How do humans and AI learn from each other? And why does training matter in both circumstances? I think these loops all have the same theme, actually, though. And throughout this talk, I think there's actually a deeper message. I'm kind of curious whether you're going to get it or not, how these loops work, and what's the underlying theme that brings them all together. So let's get started. The autonomy loop is the beating heart of an AI security system. It's the model. It's not the tool. It's the actions in a loop. Test, fail, learn, retest, and do it all again and again. In 2014, DARPA, the most advanced research organization in the US government, started asking, are fully autonomous systems even possible? And if so, what's the right way to measure these tools? I think their answer was brilliantly simple. But before I talk to you about it, I want to quantify the size of the problem that we're talking about. Now, people are looking at this in defense because they're very concerned manual effort doesn't scale. And if we think about the end game here, we can think about our local lives or we can think about our companies, but let's blow it up to entire nations. How would we secure ourselves from even the most sophisticated attackers? And if we look at the size of Japan, Japan has just 1.5% of the world's population. That means any effort that solely uses manual effort simply isn't going to scale. You're going to lose to a larger adversary. And you're not alone. The US has this problem with other countries, with China. And if everyone ganged up against China, of course, they don't have enough people. And so how do we scale it? How do we win? How do we take this to the logical extreme where we're trying to protect our systems from even the most advanced nation states? Well, I think the answer is you're going to leverage superior technology, and that's where it all began. They launched something called the Cyber Grand Challenge, and they invented this term called the Cyber Reasoning System. I think they're the only people who use it, but it's a really nice term, Cyber Reasoning Systems, the CRS. And the goal of a cyber reasoning system is to prove vulnerabilities. And the way you do that is you show that you can produce an exploit. You don't just highlight a line of code or say, I think there's a problem here. You do what a hacker does. You actually break into the system. The second part of a cyber reasoning system is to be able to remediate vulnerabilities, whether those are the ones that you discovered or ones that you discover too late after someone breaks into you. The third part of a cyber reasoning system, in DARPA's mind, was zero human intervention. These things had to work completely automatically without anyone touching a keyboard. So there's an old saying in business. You can only improve what you can measure. They put out this concept of a cyber reasoning system. The next question is, how do we measure it? So they invented a game. The game was one based around capture the flag. The idea was, instead of asking a CRS where are the vulnerabilities, they asked it to prove it. Show me, don't tell me. You had to find the bugs, patch the bugs, and most importantly, don't break anything. So imagine we have two CRSs, and they're in battle with each other, CRS1 and CRS2. If CRS1 can find a vulnerability and exploit CRS2, it gets 10 points. And then CRS2 can, of course, go and find a vulnerability and then try to exploit CRS1 and also get 10 points. But in security, it's not just about attack, it's also about defense. And so if CRS2 figures out, hey, I've been exploited, I'm going to patch the vulnerability so that it doesn't happen again, it can automatically repair the program in theory. And then when CRS1 attacks it, it fails. Gets 0 points. So far in this game, it's equal, 10 points apiece. But as I said, not everything in the world is about security. A system that is down shouldn't count for anything. You have this kind of trivial defense of just unplugging the systems, which we all know is something not practical. So how do you deal with that in the system? What they decided is to take downtime and make it negative points. If you simply turn off your program or for some reason your patch breaks the system and you can't connect, you get negative points. And so this can actually be the game winner. At the end of this game, right, CRS1 had 0 points. It did have a working exploit, but its downtime cost it, while CRS2 got 10 points for having one successful attack. So this is the game, and I think what's brilliant about it is you have to prove what you can do. You don't just tell people there's a vulnerability. You don't just say, here is a report. You actually work like a hacker. It makes sure everyone is certain. But the other kind of cool thing about this was the vulnerabilities that were being discovered were not necessarily the ones planted by DARPA. It allows for creativity in the system where if you can find a new way to hack, if you can find a new way to break into that system, you get points. There's no preconceived notion of what's right or wrong, only the measurement to see how well you did. So DARPA ran this program with this idea, and they weren't sure it was going to work. They invited the world to participate in over 100 different teams, ended up submitting, and 7 teams were selected for the final event. And one of the things I find fascinating is all the cyber reasoning systems that were submitted essentially had the same architecture. I'm going to tell you about ours, but other people worked very similar. So we have a cyber reasoning system, and the focus of them was protecting applications. And DARPA was very interested in this question of how do we protect legacy applications, and so they only allowed us to have access to the binary code. That's the compiled software with really no information from the developers, just how it's going to run. And then the cyber reasoning systems essentially would have several different agents. One of them is an offense agent that we called SWORD that would take the binary, and job was to come up with working exploits from scratch. Now, the 2 technologies that we used were symbolic execution and fuzzing. And it's kind of interesting. People ask, why didn't you use things like SAST, static analysis? And the reason came back to this way the game was scored. We weren't scored based on how many vulnerabilities we could report, only how many we could actually demonstrate. So the offense component came up with these exploits, and once the system found an exploit, it could then attack other people. Now, this is where it gets interesting, and the first twist of the story comes in. We didn't just attack people. We realized that in this world, there may be other cyber reasoning systems that are looking for attacks. After all, great hackers steal. If someone tries to exploit you, you can see that exploit on the wire, and you grab it, and you can use it against someone else. So we thought about this, and we decided we're going to add chaff. We're going to add in extra traffic to throw off other cyber reasoning systems, to make noise. There's even an amazing paper in academic called Making the Pig Squeal, essentially making any sort of system for detecting attacks too noisy to be useful. So the offense engine would then pass off that vulnerability to the defense engine to do patching. And again, everyone had essentially the same ideas. They did binary writing to go in and when there was a flaw, rewrite it and try to fix it. If there's a buffer overflow, you try to make sure it's all in bounds. They also added hardening to the binary. This makes it harder to exploit. For example, if you have a vulnerability in a piece of software, perhaps you add some randomness so that it's still there, but an attacker has to get lucky. They have to pick the right random number for it to work. These sort of mechanisms are extremely effective in practice. While they don't fix the problem, they help make it harder for someone to break into you. So this POV was passed to there. The defense agent would then create a patch, and these patches would then be fielded. But of course, before you field anything, you want to test them. We would take those patches, we would run them through and make sure, of course, it defeated the exploit, but we wanted to make sure that system didn't go down. Because remember, if the system went down, it could be as bad as never attacking at all. And so we would test those binaries to make sure that they worked correctly. And those binaries would then be given to others. One of the cool things about how DARPA decided to measure this is after you patch something, everyone got access to your patch. The idea was there shouldn't be like a secret patch, right? Maybe your patch was incomplete. Maybe you missed something. Maybe you introduced a new vulnerability. Other teams should be able to look at it. So we thought about this, and actually, the amazing hackers at CMU kind of gave us some insight into what people do. And one of the things that you can do with the binary is you can backdoor it. It was actually kind of cool. We would go and we would patch the binary so it ran completely fine on our systems. But if you tried to analyze it in one of the reverse engineering tools, it would trigger a buffer overflow and potentially wipe out another person's system. Kind of clever, right? And these are the sort of things that happen actually in real CTFs. And it's reminiscent, I think, in real life of this larger picture of supply chain attacks. What if programs work as they're intended, but they have this little backdoor that someone else can trigger? So we built DCRS over 2 years of work. In DEF CON, the machines came up live in front of the entire audience to play this game, to attack each other and defend and to see who would win. It was nail-biting. 2 years of effort for one contest. We had zero access to the keyboards on that system. What would happen? Would it even work? In fact, it wasn't just us worried. DARPA put in over $60 million US into this contest. What if it didn't work for them? So of course you know the end of the story, right? Mayhem ended up winning. This is what's called a black badge at DEF CON. It gives you lifetime entry, and this is the first badge awarded to a non-human entity. Mayhem won. It was amazing. It was able to successfully do attack and defense as well as other people, but it did it a little bit better. So I'm going to ask you, what do you think the differentiator was? Whether you're in business or national security or just a researcher, right? Generally, we fall into one of these two camps. We're the offense guy. It was finding a better exploit. We had better techniques. And to tell you the truth, this is something I was very proud of. My entire research career was in symbolic execution. And so you might think that was the case. Or maybe it was patching. Maybe we had better patches than anyone else. What do you think? Which one was it? Offense or defense? Perhaps the surprising thing is it was neither. The thing that was the differentiator, the thing that I think was the difference for why we won and why, for example, the number 3 team got number 3, was that testing engine. In real life, a bad remediation costs immediately. If you go and deploy a patch that brings your system down, you're going to feel that pain today. While a vulnerability, security is just hypothetical. If no one ever exploits it, it doesn't matter. Of course, you don't want that risk, but at some point, it is just risk. And so when DARPA was doing evaluations, they evaluated both security, functionality, and performance. When you released a patch, of course, you wanted to prevent POVs, but you also wanted to make sure you didn't break anything. And of course, you didn't introduce, like, let's say 100% overhead. And if you go back and you look at the scoreboard, the number 3 team had the same architecture we did. The big difference was we spent more time on testing. And so that's the first lesson in all this. When we start thinking about autonomous security, bringing AI to trust these systems, I think that autonomous security requires that we can do autonomous testing. And it's not something that's obvious to people. In security, we think about like attackers. We're taught that. We're taught to think about how do we prevent attacks, when in fact, the thing that prevents people from deploying things is whether it works. And so until we have autonomous testing, I think autonomous security isn't going to be used. Now, Mayhem played against the world's best hackers. Some of those world's best hackers are right here in this room, actually. It's kind of funny. So at CMU, I have the privilege of mentoring one of the world's most competitive hacking teams. These are people who run Google Threat Intel, Korea's best of the best winners, Pwn2Own champions, Project Zero, computer science PhDs, Defense Department, nation-state actors. It has it everything. So how do you think an autonomous system does against these? Do you think AI can beat the world's best hackers? Well, this is a small subset of that. And I'll tell you what, the answer was no. When Mayhem played against the world's best hackers, I think, looking back, to be generous, autonomy for things like patching was competitive. One of the things that Mayhem could do is reason about code and figure out where to insert checks, and then it could go through this control flow loop of taking that new patch, testing it, and seeing the impact, determining whether it was fit for purpose, and then fielding it, often quite faster than people. For finding new exploitable bugs, it did a reasonable job. In fact, Mayhem found vulnerabilities that PPP, the winning team here, did not find. Didn't find as many, but it found some that were different. And the reason, though, it didn't find all the ones PPP did is because hackers have this leap of creativity that machines do not have. Humans still own imagination. I don't think that's going to change. But even if we try to put it in less lofty terms than creativity, some of it came down to common sense. For example, when Mayhem played against the world's best hackers, the organizers accidentally flipped in some of the PCAP files what was source and what was destination, who was the attacker and who was the defender. And the humans immediately realized this. Oh, the labels are wrong. We'll flip the two. Didn't give it another thought. But the machine took that garbage and just ran away with it. So that's one of the challenges with AI is it can just run away, run off a cliff as fast as you can. And so I think that was the second lesson of that, is that you can't substitute creativity that comes from humans with autonomy loops. And so this gives us this idea that at the very least, you can build amazing autonomous systems, but you're still going to need those hackers to provide this thing that's very special to humans, something that machines will not replace. So after this, we were extremely excited. We had huge amounts of inbound interest because we were put there on a stage for the world to see. Hundreds of news articles were written. And so we thought, we're going to go and we're going to be rich. We're going to change the world. We started working on this problem of adoption. This is where the realities of adoption and how people adopt becomes really important in this future of AI and how we trust systems. We went out and we raised a bunch of money from venture capital in the US. This is just how you do a startup. You go out, you ask for money, you say, we're going to build a product, and it'll be the next billion-dollar business. As we raced to build this system, something that I read a long time ago I thought was really important to share with you all, and it comes from actually a Stanford professor named Dawson Engler. The Stanford professor had taken his C++ analysis tools and built a company called Coverity over a couple decades ago and sold it. And then he wrote a paper about that experience, and he had this quote: "The problems we encountered were not the obvious ones." Every year I go back and read this paper, I think you should too, because what it talks about is the difference between amazing tech and what you're going to run into in adoption. And so, after we had won the Cyber Grand Challenge, we had retrofitted Mayhem, we had gone out to market, we had done surveys, we had found out some things like people did not want autonomous patching. Happy to talk about that later. It was surprising, but they weren't willing to pay for it. And so we focused on that automatic vulnerability discovery. And the way we built Mayhem is we would take in a containerized app, and then we would leverage the power of superior computing to do what humans couldn't do. We could scale up our analysis across a dozen different CPU cores, 36 different CPU cores, or even clusters of machines to go find exploitable bugs and prove them. And of course, after we found those bugs, we would have a diagnosis step where we could tell you what the root cause was, we could tell you the CWE label, we could tell you all sorts of information, and there was a really nice UI for the user. So we built this with the money, and we'd gone out to market, and that's where actually life got very tough. Let me tell you a couple stories here. The first one is about an aerospace company where we went into the aerospace company saying, we got this great tech, we're going to find vulnerabilities. And so the way it starts out, right, is I show up after they had bought. It was a VP that had bought it. We're here to automate your security analysis. We're going to be this AI for you. Just give us your executables in a Docker container. We can scale it up, and everything will work, right? We'll do this amazing thing, because that's the way the Cyber Grand Challenge worked. And there's logical reasons for this, right? We want autonomy, so we want to use the power of the cloud. And of course, we got back, what's Docker? We don't need to use that. Our stuff's only going to run on this one airplane. And by the way, do you handle PowerPC? Because I noticed you talked an awful lot about x86. And do you handle an embedded OS like VxWorks? And we're like, yeah, those are just details. That's not a big deal. All you have to do is cross-compile. I mean, we can run PowerPC, but it's slow because we're emulating. We can run just cross-compile and Dockerizing. Why can't you Dockerize? Of course you should need to be able to Dockerize. This is just modern software analysis. Plus, you get this huge advantage of our tools will work better. You notice the problem, right? I just said our tools will work better. And so this was all frowny faces from the SVP. And so the problem came is we brought this amazing tech, but we weren't trying to meet the customer where they were. We were trying to take what we thought would be the most advanced system and then saying, hey, if you just do this lift, you'll get these amazing results. And I actually think, looking at the latest AI cyber challenge, this is also an easy mistake to make as people go to market. You assume that someone's going to come in with something nicely packaged so that your machine can do what it's supposed to do and what it does best. But getting people to that point is often the hardest part. So it came on. How long do we need to run the analysis? The person asked. I understand that you can go and scale this up, but I need to know, when is it secure? You better ask that, like, when is it secure? And I put on my professor hat and I said, well, Alan Turing said something about undecidability. So there's this infinite state space, and of course we can never say it's secure. You're gonna have to make a judgment call. And of course, yeah, sure, I'll tell my boss that. You just sold us a security tool and you can't tell us when it's secure? So that was the second mistake. My answer was technically correct, but it was useless. We have to be careful of these sorts of answers as we bring things to market. So we found bugs in this aerospace system. Valid values could cause them to crash. We thought it was a big deal, a huge proof of value. But what I ran into was kind of an odd conversation. We've proven safety. We have redundant sensors. What you just found won't matter in real life. And I was sitting there scratching my head because, at least in education, when we talk about security, we often talk about it in terms of things like safety properties. But in industry, safety means something different. They're talking about redundancy. Now, I know you in the audience, if you have the same software running on 20 systems and it has a vulnerability, you will break it 20 times, just as easy as once. But in this world, they were thinking in terms of redundancy provides that extra security. So cyber's different, right? That's what I'm saying. It's still unsafe. And again, we'll look into that. So at this point, I was really worried because so far, we weren't easily ingesting things from their system. We kind of got over that. We had to go and Dockerize it for it. We couldn't tell them how wrong to run, but eventually we found some bugs. The problem, though, was my win was not their win. And so when we're looking at autonomy, we have to think, what is their win? Is it finding an exploitable bug, or is it something different? So what saved the deal? Well, I said, by the way, one of the things Mayhem does is, as it's going and looking for new vulnerabilities, it's creating new test cases. They're here on the side. We have a test suite for 80% of your assembly code. And the SVP had the OMG face at this point. Like, what? What was that you said? 80% code coverage? And I'm like, yeah, why are you so excited? And what he told me is, we had a budget for something like $60 million to get to 80% test case coverage, and you come here and you just hand it to me? I'm super excited. And so the lesson in all this is we ended up making the customer happy. But we need to focus on their value, not ours. And so when we think about this adoption loop of AI, we can have the world's best tech, like we thought we did at that point. And every year there's new advances. But then getting that tech into an organization is a completely separate loop we have to look at. We have to look at when we deploy it, can people adopt this technology? We have to listen really carefully to what they're saying and make sure that we prioritize things based on their value and adjust what we're doing. And then, of course, updating our products and fixing them, not just assuming that what we have is going to work out of the box. And getting these sort of adoption loops currently is very human-centric. Nowhere in there did I talk about advanced AI, but if I hadn't gone through this loop, that customer would not be using Mayhem today. So the third loop I think that we need to look at for AI and trustworthiness is this improvement work. Continuous improvement in humans and machines. So as I mentioned, I am extremely fortunate at Carnegie Mellon that in many ways some of the world's best hackers just show up. And so we have this question, will AI replace these? And some people think, well, we just need to train AI correctly. And even with humans, there's this idea that I think some people have, that if you, for example, come to the right school, you get into a Harvard or an MIT or Carnegie Mellon, you're going to run into this Yoda. And this guy is going to sit on your back and teach you all the secrets. They're going to have all the answers for you. But this is very romantic. It's a great story, but it's not real. Instead, the way you get good at something is through deliberate practice. All the research in the world shows that there's really 5 things for continuous improvement and for mastery of a particular discipline, whether you're playing violin or piano or sports or hacking. What you have to do is at every point, you have to be focusing on a specific skill you want to improve, and you have to pick out a specific goal. If it was music, maybe it's playing arpeggios at a certain beats per minute. You need to get timely feedback as you're practicing to see if you're practicing correctly. Are you making mistakes? This is really easy to do, relatively speaking, in music. Relatively difficult to think about when you're hacking unless you're very careful how you do it. And you need repetition. Explaining something to people once is not enough. They need to experience themselves again and again to the point where it becomes second nature to them. And after something becomes second nature, there's increasing difficulty. You ratchet up a bit. And you just keep doing this again and again. So you go from a level 1 hacker, skill, goal, feedback, repetition, difficulty. Then you become a level 2, and a level 3, and a level 4. And every hacker I know doesn't turn to me as the Yoda to do this. Instead, what they do is they turn to capture the flag. And if you think about it, while we call capture the flag this kind of interesting name, it's a game. We think about it, it's gamifying security, and that's why it's cool. Really what it is underneath the hood is deliberate practice. You have your specific skill. For example, in this challenge, our specific skill is binary exploitation 101. You have a specific goal. How many bytes are needed to overwrite the return of this function foo? And you get timely feedback. When you enter in what you think is your answer and you hit check, you're either right or wrong, and it will tell you. Now, as you play these games, you pick an area like binary exploitation, you have repetition, you have several 100-point problems. And then when you master 100-point problems, you start going on to 200-point problems and so on. And at some point, if you keep doing this, right, you forget how hard a 100-point problem was the first time you did it. It becomes easy. And so you master this as you elevate. In fact, you might expand out then. You might look at network security, web security, crypto, whatever the area. We can apply this idea of repetition and graduated difficulty with deliberate practice to get better and better. So this is how humans work. They have this feedback loop, and it's very deliberate. Can we use that to teach AI? How do we teach AI to hack? And once we teach it to hack at level 1, how do we get it to level 2, to level 3, to level 4? Now, the way we originally trained AI, and I'm talking here specifically about LLMs, was these big companies essentially downloaded the world's data, and they did a statistical analysis over it, and used this as a next token predictor. That won't work for AI for computer security because, well, if we follow this idea, you'd be training on something like a CTF write-up or a pen test report. And what that AI would come up with is the next token predictor. It would essentially be guessing the next word to emit, not the next action to take. But there is a solution, and this is what's really interesting when we look at what's going on in research, is using CTFs for something called reinforcement learning. Reinforcement learning is exactly what it sounds like. It's deliberate practice. When you get a question right, we give the AI a reward, just like you get that little jolt when you get a security question wrong. And so you give AIs these CTF problems, and you ask the models to try to run, break, and learn to get the flag. And the cool thing about this is when they get the flag, you know it got it right. We worry about things like AI hallucinations. Here we have a built-in check. It doesn't matter if the AI hallucinates. It's either the right flag or not. So RLs train agents to carry out actions and solve problems. The way this gets set up is you can take a CTF server, for example, and you can take your LLM and put your LLM in an environment, something like Kali Linux. And you can do this today. You can download Claude for Code and put it in Kali Linux and pretend it's a little student there. And then you give it a challenge. For example, that binary analysis 101 problem. And you ask the LLM, can you solve it? And it will try to solve it. And as it tries to solve it, you ask it, did you get the right answer? And that is your flag. The LLM gives it to the grader, the flag checker, and it can decide, did it do it right or do it wrong? So what we see here is an amazing parallel between how we train the world's best hackers and how companies using reinforcement learning are training AI. In fact, Anthropic has spent a lot of time doing exactly this. If you went to DEF CON this last year, there was a great talk from someone named Keen Lucas, where he had used Claude, put it in Kali Linux, and unleashed it across CTFs, and here are the results. When Claude played Pico CTF, the high school hacking contest for beginners that I run, it was able to be in the top 3% globally. When it competed in the humans versus AI challenge, it solved 19 of the 20 challenges. In the Airbnb CTF, it got 15 of the 20 challenges solved. And so what we see is AI is getting to this point. Can it beat the world's best hackers? Well, right now, it's about easy medium. If you put that same AI in a real competitive hacking contest, something like Plaid CTF, which is a DEF CON qualifier, you put it in DEF CON like Mayhem was itself, they get 0 out of 0. So, can AI beat the world's best hackers? The answer is not yet. But again, I think that's the wrong question. The right question is when AI can play in Plaid CTF, when it wins at DEF CON, what do we need to do to trust it? That's been the theme of this talk. Because we know that one of the challenges with AI today is it doesn't know how to fail. For example, this is taken from Keen's presentation. When Claude got frustrated, it didn't say, I can't solve the problem. It didn't try harder. Instead, it would just say very confidently, here is the right answer. Or the actual flag would be here, and you would ask Claude, did you figure out the problem? Yes. Did you get the flag? Yes. Did you check it with the scoring server? Yes. It was lying the whole time. Or worse, I told you in DEF CON and in CGC, I think the reason we won was this testing loop. This is something that these AI, when you let them go completely autonomous, often get wrong. For example, Claude's in its final notes in one of the CTFs was, the complete system crash might be the ultimate defense. Surely you've heard a security expert say that you can just unplug it. Or wire snippers, right? Cutting the Ethernet cable is the most effective defense. It may be logically true, but it's useless. It's one of those answers right there. So remember, in the face of imminent attack, a complete shutdown is better than a compromised system. This is what's going to happen if you place AI and replace all those humans today. So I think the lesson out of this is you can use these same ideas to train humans and to train AI. But the thing that we need to work on is build-in failure checks, because the AI might not tell you. In fact, when you're trying to use reinforcement learning, this is actually, in some ways, in my experience, one of the more tricky things to get right, is how much what we call hallucinations are lying. How do you check to make sure that it really did what it was supposed to do? I'll tell you, it even goes a step further than this. It's not just things like guessing flags. If you tell an AI, don't access the source code, solve this problem without it, but it could access that source code, it will start accessing that source code. So I asked, do we trust AI? Will we be able to trust AI in replacing the world's best hackers? And I told you that I think there's probably a uniting thing. We have these 3 loops. There's the autonomy loop. What does it mean to actually build systems? We have this adoption loop. How do we get those technologies to actually be used in companies and not just scientific experiments? And then the learning or training loop. How do we make them better and better? What brings these all together? What do we need to do so that we can trust AI? Did you figure it out? So this talk really wasn't about success, right? This talk was about failure. In Cyber Grand Challenge, one of the things that Mayhem won, it was almost accidentally, we didn't plan on it as being a big differentiator, was knowing when no fix was better than a bad fix. It was failing to produce something more secure, but being okay with that. When I talk about the company, I could give you hundreds of examples where initial adoption failed. We brought an amazing technology to market. We've been successful. In fact, I'm happy to announce that we were acquired by a company called BugCrowd just about, October 24th, not that long ago. So we were a successful startup, but that pain of being able to come up with an adoption loop is real. And as far as I can tell, that's something people aren't focusing on today. And then finally, in CTFs, it's harnessing failure to learn. Now, since you're all hackers in this shouldn't be a surprising. Most of your life is spent on failure. It's trying to figure out why something isn't working, why your attack is not succeeding, or how to get into some place, and you haven't quite figured out the right angle yet. And so I think the answer to how do we trust AI is to trust AI, hacking in the real world. We need to make failure visible. We need to make it controlled. So the question isn't this parlor trick, will AI beat George Hotz? I'm sure there will be a Gary Kasparov moment with Deep Blue. It's how do we see when AI fails? How does AI learn from that failure, and how is that failure aligned with our goals? Not its loss function of saying it got the right flag when it really wanted to bring down the system. So if you think about it, do you agree? Is this the right uniting seam? I'll leave you with that. Thank you.